Assalamualaikum and hi everyone. Now I would like to continue our lesson on chapter 3, which is electric current and direct current circuit. As far as I was concerned, we have been learned some topics from these topics of the chapter, which are from subtopic 3.1 to subtopic 3.5. So from now onwards, I will going to continue starting from the subtopic 3.6. Okay, for this subtopic 3.6, the Kirchhoff rules, the learning outcomes is to state and use Kirchhoff rules. First, we need to identify or know the terminology of this circuit or this Kirchhoff. Okay, first is the node. Node is a point or junction in a circuit where three branches converge or more components are connected. A branch represents a single element in a circuit such as voltage source or resistor or load. Loop is a closed loop or closed path in the circuit. It's any closed path in the circuit. Whereas for the voltage drop, the potential difference between any two specific points of an electrical conductor. Okay, the first rule for this Kirchhoff is we call it the Kirchhoff first rule, or junction or current rule, and also we call it the Kirchhoff current law. Okay, it states that the sum of the current entering any junction in an circuit must equal to the sum of the currents leaving that junction. Or in terms of the equation, the sum of current in I in equals to the sum of current out of I out. Equation 3.16. For example, we have the node here, the point of junction A, okay, and then the point of junction B. Okay, the current that flows into this junction, into this point is I1 and I2, and then the current that flows out from this junction is I3. And then for the point of B, let's say the current that entering to the point B is I3, and then we have two current that goes out from the point B is I4 and I5. So we have the equation here. Okay, for the first junction, for the junction A, we have the equation I1 plus I2 equals to I3. So here is the equation, and then for the junction B, okay, we have the equation of I3 equals to I4 plus I5. And then for this two junction, we can have the summarization, which is the summation of current in that junction equals to the summation of the current out from that junction or from that point. Okay, the second rule for the Kirchhoff is used for the loop or voltage rule, and also it's called the Kirchhoff voltage law. It states that in any loop, the sum of EMF is equals to the sum of the product of current and resistance. So in terms of the equation, here we have the sum of EMF is equals to the sum of the product of current and resistance in the circuit. Okay, for this one, we need to have the sign convention. This kind of convention is very useful in order to examine or to analyze the circuit by using the loop or using the Kirchhoff, either the first rule or the second rule. Okay, the first one, if we have this kind of the direction of the loop to the right side, and then here the EMF is also to the right side, minus in the left and plus in the right side. So here we can have the direction of the loop is same direction as the EMF. So now we will take the sign convention for the EMF is plus EMF. Okay. Whereas for the if the direction of the loop to the right side, whereas for the EMF to the left side. So that means it's opposite direction. So the sign convention for the EMF is minus E or minus EMF. For the product of IR or the product, that means for the voltage drop across any element in the circuit, if the direction of the load to the right and the current also to the right side, so we'll have the positive IR. Okay, whereas if the direction to the right side or to the right and then the current it flows to the opposite direction, so we will use the sign convention here is minus IR. Okay, so we have different side of the sign convention. Okay, where either plus IR or minus IR. Okay, problem strategy for the Kirchhoff laws. Okay, how we are going to examine the circuit. We have some tools. Okay, the first one, choose and labeling the current and any junction. Choose and labeling the current at each junction in the circuit. And then the second one, choose any one junction in the circuit and apply the Kirchhoff current law or Kirchhoff first law. And then the third one, choose any two closed loops in the circuit and either it designated a direction clockwise or anti-clockwise, it doesn't matter. Okay. And applying the Kirchhoff voltage law. So the first one applying the Kirchhoff current law and the second one applying the Kirchhoff voltage law. Then we can have the analysis of the circuit. And the last one, solving the simultaneous equation to determine the unknown current or unknown variables that we need to determine. Okay, so we have now we have the step 1, 2, 3, 4, 5 step in order to solve any circuit by using this Kirchhoff law. Okay, either the current law or voltage law. For example, consider a circuit that figure 3.17 at the bottom here. Okay, alright. We have one loops. Okay, two loops and three loops. Okay, we have three loops in the circuit. That means we can solve this circuit to determine any variable in the circuit by using these three loops. Okay, look at one by one. At the junction A or D, we apply the Kirchhoff first law, where the summation of current in equals to the summation of current out. At the point D here, we have the equation for the Kirchhoff current law. Okay, where the I1 equals to I2 plus I3. Okay, it also happen with the point of D, same as the current in equals to current out. Okay. Alright, so for the loop 1, look at the loop 1. Alright, loop 1 there. Loop 1 is from the alphabet of F, E, D, A, and F. Okay, loop 1. So we will examine this loop by using the Kirchhoff voltage law. Okay, the summation of EMF equals to the summation of product of I times R. Okay, from here you follow the direction of the loop from right side here to the left side. It follows around. Okay, EMF number 1. Okay, and goes through to the EMF number 2. Same direction and same direction of the EMF. So now we have the E1 plus E2. Okay, then equals to the product of I times R. Okay, current that flows through R2 is I2. Okay, here. And then current flows through the R1 is I1. Okay. Okay. There is only two resistors in the circuit. So now we have the summation of EMF in that loop equals to the summation of the product of I times R, or we call it the voltage drop. Here is the voltage drop usually in the circuit, voltage drop. So this is the equation number 2. Okay, then for the loop number 2, okay, which the notation of A, B, C, D, A. A, B, okay, C, D, and again A. Right. So for the loop number 2, look at the loop here, the direction of the loop. Okay, we have the equation of summation of EMF equals to summation of product of I times R. Okay, look at the loop. The loop here, yeah, from the right side to the left side also. Okay, is follow direction here. Okay, for the E2, since the same direction for the loop and then for the EMF, so the E2 is plus, right? Plus now. And then for the E3, okay, it follows here. Okay, E3. Right, look at the E3. The direction of the E3 is differs or opposite direction with the direction of the loop. So that's why the E3 direction is minus. Yeah, okay, here we have the minus E3. Okay, equals to the product of current times the R. So here we have the two resistors here, R2 and R3. So the I2 times R2 plus, the minus I3 times R3, because of here same as this one. Why the I3 times I3 minus? Because of the direction of the current now different or opposite direction of the loop. Okay, that's why it has the minus sign of here, right? So now we have the equation of the second loop. Okay, now the third loop. On third loop, in the direction of F, E, C, B, and F, okay, we also have two resistors here, and then we have also two EMF here, EMF number 1 and EMF number 3. So we will develop the equation for the, here we have the summation of EMF equals to the summation of product of IR. Okay, look at the direction of the loop. Okay, from top here, direction of the loop from the right to the left, and also happen with the EMF number 1. So that's why plus, and then it goes through here. Okay, see the direction of the loop to this side, and then direction of the E3 also that side. So it's plus also. So E1 plus EMF number 1 plus EMF 3 equals to the product of I times R. For the this one R3, the current flows through R3 is I3 and is same direction as the loop number 3. So it's plus. And then for the resistor R1, look at the current that flows through the R1. Okay, this current is flows the same direction as the loop also. So the product of IR here is also positive. So that's why we have the question here. The EMF 1 plus EMF 3 equals to I3 R3 plus I3 R1. So now, in order to solve to determine any of the parameters in this circuit, we solve the equation 1, okay, 2 until 4, and any of the equation from the also. Then we can have the current in the circuit can be determined. Okay. The most important is we need to derive the loop equation first. Okay, from the first one KCL or Kirchhoff current law to the Kirchhoff voltage law, then we have three types of equation because we have three loops. Okay, not that from the calculation, sometimes we will get the negative value of the current. The negative value is not the value, actually it's the indicate, that's the sign. In the sign, the direction of the actual current is opposite direction with the current that drawn. Okay, it's just the direction of the current, it's not the value. Although we had a negative sign, this indicate that the value indicate the direction of the current, okay, is opposite direction to the current drawn. Now we will try to look to the example. Okay, example 3.12 here. From figure 3.18, we have one loop here with resistance 8.50 ohm, 6.22 ohm, and 15.1 ohm connected in series with the EMF or supply 11.5 volt and then 15.2 volt. Okay, we will apply in the Kirchhoff second law or the Kirchhoff voltage law. The summation of EMF equals to summation of the product of IR in the circuit. Okay, for the EMF, look at the direction of the loop. Direction of the loop flow from right to the left for this one. So it's same direction for the loop N for the EMF. So it's plus, and then the direction for the loop and also direction for the EMF for the second one here is also the same. So it will be plus, right? And then for the product of IR, the I that flows through the resistor 15.1 is I, and then followed by 6.22 here, and then followed by 2 ohm here. It's the 2 ohm here is the internal resistance in the battery, in the cell, and internal resistance in the cell. So we need to plus up also in the equation. So here we have the 2i plus 8.50i and plus 4i. So the total up for the current that flows in the circuit now equals to 0.74 ampere. So now we already derive or get the final answer for the current 0.74. The direction is anti-clockwise. Okay, look at this example. This example is more complicated actually. We have the circuit of figure 3.19, okay, and this combination of series and parallel circuit. Okay, series and parallel circuit. We have two supply in the circuit for the 12 volt and 9 volt. We need to determine the current I1, I2, and I in the circuit. B, the potential difference across the 6.7 ohm resistor. C, the power dissipated from the 1.2 ohm resistor. And D, the last one, the potential difference between the point X and Y. Okay, look at the solving process here. Alright, we will identify by using the loop. Okay, at the junction A here, by using the Kirchhoff first law, Kirchhoff current law, okay, we know that the current that flows into this junction is I1 and I2, and the current that goes out from this junction is I. So we have the equation here, the I1 plus I2 equals to I. Okay, and then we're using the second law of Kirchhoff law. For the loop number 1, the summation of EMF equals to summation of product of IR. We have the equation here. A12 equals to 3.9 I1 plus equals to 3.9 I1 Okay, 3.991 followed by 1.2 here, I, and then followed by 9.8 I1. So here we have the equation, the first equation for the loop number 1. Okay, and then rearrange the equation, we will get the 13.7 I1 plus 1.2 I equals to 12. For the second loop, look at the second loop. We have the equation here. The second loop is here actually. Second loop is here. So the EMF, summation of EMF equals to summation of product IR. We have there here the direction of the loop this side. So we have the 9.0 equals to 6.7 I2. Where is it? 6% I2 plus 1.2 here I. So now we have the equation for the second loop, 6.7 I2 plus 1.2 I equals to 9.0. By arranging the equation and by solving the simultaneous equation, we will get the answer for the I1 equals to 0.72 ampere, I2 equals to 1.03 ampere, and I equals to 1.75 ampere. You can use your calculator, equation in the calculator, and then you will get this answer for the I1, I2, and I. Okay. B, we need to determine the potential difference across the 6.7 ohm resistor is given by equation V. The voltage drop across resistor 6.7 is V equals to I2 is 1.03 times 6.7. The answer will be V equals to 6.9 volt. Okay, C, the power distributed from the 1.2 ohm resistor, we use the equation of P equals to I square R. Okay, substitute the value for the current and the R. Current is 1.75. This is the total current. Square times 1.2 for the R of 1.2 ohm. So the answer for the P, power distributed from 1.2 ohm resistor, is 3.68 watt. Okay. Then the last one, the potential difference between the point X and Y. Okay. Okay, from here you can see that the direction of the current to the left and the direction for the EMF is to the left side also. So the V of X and Y equals to Vx minus Vy. Vx is the final state and Vy is the initial state. And the electron travels from Y to X because electron travels from Y to X, but the current travels from X to Y. It's opposite direction of the electron flow. Okay. So we will put the number in the equation. For the Vx is minus 9.8 times I1 plus 12 for the EMF minus 3.9 I1. Why it has minus here? It's due to the direction of the electrons. Okay, now the answer will be Vxy equals to 2.14 volts. Okay, that means the potential difference between X and Y, the X is more positive than the Y. Note that the direction of electrons flows in the opposite direction with the current. Okay, that's why we have the plus IR and vice versa. Direction of the electron flows in the same direction with EMF, so thus we have the plus EMF and vice versa. Okay. Alternatively, we can have a look to find to calculate the value for the V, X and Y by using this equation. Okay. Vxy equals to Vx minus Vy also, but this one now we use the equation, the relation of 3.9 only. Okay. We have the equation here. The Vx equals to Vxy equals to 2.1 volts. Okay, and then we can have another alternative. Okay, Vxy equals to Vx minus y, but we use the equation, sorry, the value of result 1.2. Okay, so we have here the value for the Vxy is 2.1 volt, also 2.1 volts. Okay, look at the differences, the value of Vxy. Okay, the final value is different, it doesn't matter, but the most important is the process or the concept. If the concept is there, that means the correct concept, then the answer of the final answer, it might be differs more or less. Okay, it doesn't matter. Okay, so that's how for the Kirchhoff rules. Hopefully that you understand enough for the Kirchhoff rules. Now I'm going to continue our lesson for the subtopic 3.7, which is the electrical energy and power. First, we need to identify the meaning of the electrical energy. The electrical energy is ability to do the work or to move charges. Now, consider up we have a circuit consisting of a battery that is connected by wires to an electrical device such as a lamp, motor, or battery being charged as shown in figure 3.20, where the potential difference across the electrical device is V. Okay, the current flows from the positive supply to the negative supply, and it will creating the potential difference across the AB. When the current flows from the terminal A to terminal B for time t, the charges in which the carries from B to A is given by equation Q equals to I times T. And then the work done to bring out this charge from B to A equals to the electrical energy supply is given by equation, but W equals to Q times V. And then if we substitute the Q in the equation, we will have the equation of W equals to E equals to V I T. And because of Q now equals to I T, so it is the Q. If the electrical device is passive resistor, device which converts all electrical energy supply into the heat, so the heat dissipated H is given by equation H equals to W equals to VI. It's just the passive component. Or we can have the equation H equals to I square R times T. Or we can also use the equation of H equals to here, I put here, equals to V square R times T. Times T, yeah? Right. And then power, abbreviated by P, is defined as the energy liberated per unit time in the electrical device. The power that supplied to the electrical device is given by equation P equals to W over T, and W is VIT. We will substitute the VIT in the equation, so here the T can be cancelled out. Now the power equals to IV. P equals to IV, the current times the voltage. When the electric current flows through wire or passive resistor, hence the potential difference across it is V equals to I times R. It follows the Ohm's law. And then we can have a look to the electrical power can be written as P equals to I square times R, or P equals to V square over R. The unit for this power is watt. Example for this subtopic here, for the figure 3.21, suppose that we have the resistor connected with the EMF. It has the internal resistance of small r. Okay. In figure 3.21, a battery has an EMF of 12 volt and an internal resistance of 1.0 ohm. Determine the rate of energy transferred to electrical energy in the battery. B. The rate of heat dissipated in the battery. C. The amount of heat lost in the 5 ohm resistor if the current flows throughout it for 20 minutes. Okay, let's look to the solution. Okay, we take out the information that given in the questions. The EMF equals to 12 volt. Internal resistance is 1 ohm and R or external resistance is 5 ohm. The current in the circuit is given by equation EMF equals to I times bracket R, capital letter of R, plus the small letter of R, internal resistance. And then we substitute the number in the equation, we get the answer for the current flows in the circuit is 2 ampere. Okay, now, the rate of energy transfer to electrical energy or power in the battery is given by equation P equals to I times EMF. So we have the final answer here for the power or energy that transferred to the circuit by the battery is 24 watt. B. The rate of heat dissipated due to the internal resistance is given by equation P equals to I squared times R, the small letter of R, which is the internal resistance. So just put the number in the equation. The I equals to 2 square times the internal resistance is 1. So the answer will be 4 watt. For the C, given the T is 20 minutes times 60, so the time taken of the current flows in the circuit is 1200 seconds. Then the amount of heat loss in the resistor is S equals to I squared times R times T. Just substitute the number in the equation. For the I 2.0, R is 5, and then T is 1200 seconds. So here we have the amount of heat loss in the resistor is 2.4 times 10 to the power of 4 joule. This is the answer for the question number C. Subtopic 3.7.3, combination of cells. If we have the cells that connected in series, we will determine the value for the EMF and also for the internal resistance. Okay, if we have two types of the EMF that has the internal resistance, EMF1 with the internal resistance R1, and then EMF number 2 with the internal resistance of R2. So since the connection is in series, so we have the total of EMF and the total internal resistance R for this connection is given by equation 3.22 and 3.23, which is the for the EMF, the total EMF equals to EMF1 plus EMF number 2, since the connection is in series and the same direction. And then for the R, the total resistance for this connection is R1 plus R2. This one is followed the resistors in series. Note that if one cell of EMF E2 says it turns around in opposition, that means it connection in different way in opposite direction between the between the EMF number 1. Okay, so we have the total EMF equals to EMF number 1 minus EMF number 2. Okay, but the total internal resistance remains unaltered, means it's not changed. That means the total of internal resistance is just plus up, it's not unchanged. or the cells in parallel. If we have two cells connected in parallel, in figure 3.23 there, the total EMF and the total internal resistance R is given the equation the EMF, total EMF equals to EMF 1 only. Okay. And then for the total internal resistance, we use because of the connection in parallel, then the equivalent resistance is 1 over R equals to 1 over R1 plus 1 over R1 also. So it follows the connection for the parallel resistors. Okay class, that's all for the subtopic 3.6 and 3.7. Okay. Hopefully that you understand all about that topic. All the best. Thank you very much.